In this video, I'll discuss how to make use of the advanced hardware and infrastructure you learned about in the last unit. First, we'll talk about standard high-performance computing workflows and how to identify them. With that in mind, we'll break up how to scale up machine learning into training multiple models at once and training one big model. When we look at scaling up an application, we often categorize it into one of these common high-performance computing or HPC workflows. The workflow that goes with your application depends on the structure of your code and how it can be broken up to run components in parallel, but also the hardware that you have available. In general, the workflow that goes with your application will determine how easily you can scale. Often, different libraries and software provide solutions for different workflows. The first of these is high throughput. High throughput applications are those which have fully independent computations. Thinking programmatically, this would often look like code that could be written as one big for loop, where each iteration is not dependent on the one before. You can scale by running multiple iterations at the same time in parallel. In a throughput application, you can usually get the most speed up, or take the most advantage of additional hardware. This is because each process does not need to communicate with any other, and there is little to no redundant operations being done by each process. If you've heard the term embarrassingly parallel, or as we like to say, pleasantly parallel, this is referring to high throughput. MapReduce applications build on throughput. It refers to the process of mapping an operation on a number of inputs, and then performing a single operation on the output of each input to produce one result, the reduce step. The map step can be broken up just like a throughput application. The reduce step is done by a single process and can either be done by one of the map processes after the map step is complete or by an entirely new process that starts up after. The first two workflows are called data parallel. You are running the same operation or task on a number of different inputs or data. The next workflow refers to task parallel applications. In this case, we are potentially running discrete tasks simultaneously, sometimes in multiple languages, with varying resource needs at each step. These applications tend to be fairly complicated and often require more work to get running. Finally, we get to the fully parallel models. When applications cannot run fully independent, we call them parallel. These applications involve some amount of communication between processes, which takes time and can decrease the amount of speed up you can get. We can categorize these into two workflows, shared memory and distributed memory. Shared memory parallel is where every process is on the same computer. In this case, communication happens using the memory space on that computer, hence the name shared memory. If you've heard of multi-threading, that is a shared memory model. Shared memory applications are limited by the memory and number of cores available on a single computer. In a distributed memory application, each process can run on a different computer, which is why it's called distributed. Since computers can't see into the memory of other computers, when the processes have to communicate, they do so over a network connecting the machines together. HPC clusters, or supercomputers, have been optimized for this type of application and have very fast interconnect between nodes, or computers. Distributed applications are limited by the scalability of the application, not necessarily the hardware. Before we take a closer look at how to scale machine learning applications, let's go over a few examples. These are based on a word count problem. We have several documents stored in files, and we'd like to get a summary of what they contain. To do that, we get the top 5 words used in each document. The two questions you want to ask yourself to identify an HPC workflow and figure out how to parallelize an application are, where is the independence, and what data access patterns do you expect? In this problem, we have one main operation, counting words. This operation can be done independently for each document. As far as data access goes, each file is read from the file system, counted, and then perhaps the result is written back to the file system. Since this entire process is independent, this is a throughput application and can be split up completely. Now, what if we wanted to get the top 5 words across documents? The initial word count step is still independent, but summing the counts from each book is not and has to be done in serial. For that to happen, the data from each process in the count step has to go to the process doing the merge. This is a MapReduce application, where the map step is the same as the throughput application we had before, and the reduce step involves summing the counts from each document. Finally, let's take it a step further. We want to know which words are unique for each book by dividing the count for each book by the overall word count. We'll call this the normalized word count. We could do this as a MapReduce application like we did before, but there is an additional step at the end that is independent, assuming each process has the overall counts. This is a parallel application. Each process can count the words in each book and send their counts to process 1, who does the merge. Process 1 then sends the overall counts to process 2 and 3, who can produce the normalized counts and write out the result. Next, we'll start applying our workflows to machine learning applications. Remember the first word count example we went over? Imagine instead of counting words, we are training models on different hyperparameters. Just like word count, we can train each model independently given a list of hyperparameter combinations. For each one, we may want to train the model, calculate loss, accuracy, or other metrics, and save the model and metrics to a file. This is a throughput application where we can train each model on a different process. On your own computer, you can start up multiple Python processes and have each train on a different subset of parameters. Without going too deep, on an HPC cluster, you can use something called a job array to do this. We can take this a step further and cast it as a MapReduce application. Once we have trained the models on all the hyperparameters we're interested in, we may want to do some sort of gather or reduce operation. We may be able to programmatically determine which model we like best based on our metrics. Or we might want all models with a metric above or below a certain threshold, or perhaps rank them to take a closer look at interactively later. In all of these cases, we can use a MapReduce framework to accomplish this task. Now let's look at distributed training, that is, training a single model with more hardware. This is impossible to do independently on many different processes, and so it is a fully parallel problem. Why would we want or need to do this? There are 2 reasons. First is the size of data sets. Deep neural networks in particular require a lot of data to perform well. Here are a few common data sets used in neural network training and their respective sizes. The Microsoft COCO dataset is a modest size at 18 gigabytes, but many other common image datasets, like ImageNet and the MIT Places dataset, take up hundreds of gigabytes. The Moments in Time dataset, which contains 1 million short videos, totals 10 terabytes of data, or 10,000 gigabytes. For reference, the GPUs that we currently have on our system have 32 gigabytes of RAM. In order to train these large datasets efficiently, we have to be able to break up datasets across different GPUs on different computers and train the same model. The sizes of models are getting larger as well. The state-of-the-art convolutional neural network models have hundreds of millions of parameters and take tens of billions operations. That makes DNN models difficult to deploy on embedded systems with limited resources. To make a model generalize better, it tends to be larger. This can also stress the GPU memory size and may require splitting the model across multiple GPUs on different nodes. How might we do this? Here are a few ways in increasing complexity. The easiest thing to do is to distribute training on multiple GPUs on a single node or computer. This is part of the core functionality of Keras and PyTorch. In Keras, you can use the multi-GPU model functionality, and in PyTorch you would use the data parallel class. Next, for large datasets, we may need to expand to multiple GPUs on multiple nodes. This is called data parallel because we are splitting up the data, but each GPU has a copy of the network. For each training step, each node will train on its subset of data, and the model updates are synced across nodes. You can play with how you break up the data and how often you sync the updates for the model. For TensorFlow, this is implemented by the Horovod package, which was developed by Uber. PyTorch has a submodule, Distributed, with a data parallel component. Finally, we have task parallel, where we are splitting up the operations in the problem rather than the data. There are actually two cases where this is prevalent, for the large model case that we saw on the last slide, but also for reinforcement learning. In reinforcement learning, the model itself is relatively small and does not need to be broken up, but it may have many observers or simulations running on different nodes that collect data to feed back into the model. Again, we have a few options for implementations or frameworks that we can use. PyTorch has distributed RPC, which stands for Remote Procedure Call, which is where a program causes a procedure to execute on a different node. This can be used for both distributed model training and for reinforcement learning. Ray is a general-purpose framework for distributed machine learning and has backends for both TensorFlow and PyTorch. Ray is mainly associated with reinforcement learning, but also has components for hyperparameter tuning and data parallel training. This concludes our lecture on advanced computing and hardware. It's an exciting and quickly evolving field, and I hope we have given you a taste of what's going on. In the overview, we discussed major trends in advanced computing and hardware. As the fields of machine learning and AI grow, there has been an increased reliance on advanced software, algorithms, and hardware architectures for performance improvements. There are many new hardware interfaces and platforms becoming available, and a lot of open source computing environments. We then went over some of the common languages used in machine learning: Python, Julia, MATLAB, and R. After summarizing the properties and some of the popular packages of each, you saw a quick demo to give you a feel for what each language looks like and has to offer. Then we showed some of the commonly used frameworks used to train neural networks. We described some of the more common ones, and you got to see one of them, Keras with TensorFlow, in action. In this demonstration, we showed how to take a notional design for a convolutional neural network and write a program that will build that network, train it, and then evaluate it. We learned the various components that form a computer, including a high-performance computing system, and that the choice of the hardware used for AI, and in particular machine learning, has a critical impact. We examined the underlying operations used in machine learning algorithms and why they are well suited for specialized hardware such as graphical processing units, or GPUs. Because of the recent advancements in these computing technologies, machine learning algorithms have become tractable, enabling exciting new research directions within AI. Finally, in this module, we showed how to make use of the advanced hardware and infrastructure and scale up a machine learning problem. We described the different types of applications or workflows that must be identified when scaling, and showed which machine learning applications fit these workflows. We ended with a discussion on the different types of distributed training and some of the available software to make it happen.